Hello friends, welcome to the next lecture in the series Thermal History of the Universe. So we will look at two useful relationships today. One is the continuity equation that we will be using a lot, and you must have seen this before. So this is rho is density and h is the Hubble parameter, p is the pressure, and dot means time derivative of density plus 3 times Hubble parameter multiplied by rho plus p is equal to 0. This is the continuity equation, and you should have seen this before. Next useful relationship which we are going to look at today is dp over dt, capital T, which is temperature, is equal to partial derivative of P with respect to temperature is equal to pressure plus density divided by temperature. And we will take advantage of this approximation that mu, chemical potential of all particles at all times, is much smaller than temperature. This is mentioned in Doddelson, and we will take advantage of this statement when proving this relationship. Now, what is P? P, pressure, is a function of time and hence a function of temperature, because temperature is a function of time. And in isotropic universe, P does not depend upon position, does not depend upon direction in isotropic and homogeneous. So it is same everywhere. Only thing that changes P is the time. So P is a function of time and hence a function of temperature. Therefore, partial derivative of P with respect to temperature is equal to full derivative of P with respect to temperature. Now the relationship for pressure is this, which we have seen before. And when I take its partial derivative, I will, with respect to T, I can write this as, and by the way, expression for F is this, which is you should have a plus minus sign here, and one second. So yeah, so we should have plus minus sign here, plus minus, and E is equal to square root of m square plus p square. Partial derivative of P with respect to temperature now becomes, I will leave F as it is, and partial derivative of capital P with respect to temperature. F is what depends upon T, and therefore it will be partial derivative of F with respect to temperature. And now what is partial derivative of F with respect to temperature? Here you see that I can derive this relationship. I have used Mathematica to replace partial derivative of F with respect to T with in terms of partial derivative of F with respect to E, and it comes out to be minus E over T minus this df over dt is equal to minus E over T multiplied by df over dE. So this df over dt I replace with this thing, and then I get this. Now this df over dE I write as df over dp multiplied by dp over dE. And what is df over dp? So I have df over dp and dp over dE. So what is dp over dE? And when I this is expression for energy. So partial derivative of energy with respect to P is this. Therefore, this expression becomes this would become df over de is df over dp over de, and this is p uh, p over e. This is e. So this will become e over p. E over p. Reciprocal of this. This is p and this is energy. P over energy, momentum over energy, and reciprocal of this will be energy over p. And now we substitute all the values in this integral. We get p square over 3t, and df over de is replaced with this, and then we have d cube p, and next is we write d cube p as 4 pi p square dp, and when we do that, the integral limits become 0 to infinity. So it's all simple calculus algebraic manipulation, nothing fancy here. And then we factor out minus g over t 2 pi whole cube. 4 pi also comes out, becomes minus g over 6 pi square, 0 to infinity. And I have this ep cube over t, which I am calling now ap, a as a function of p, and del f by del p, and multiplied by dp. Now this is for a given temperature. This is a function of p. AP is a function of p for a given temperature, and now I am going to integrate it over all possible p values, and that integral I am calling I1. So I1 is this integral of AP df over dp and integrating over all possible values. When we integrate overall, we can integrate by parts. So this is a, and this we can call b. Df over dp we can call b. So we have ap, and then integration by parts we get f minus 0 to infinity dA by dp, and then fp dp. This is integration by parts. Now look at the first term here, apf 0 to infinity. Now when p is infinity, when p is infinity, then what is fp? You can look at this fp expression, and then you can see that, by the way, this is plus minus 1. So look at this fp expression and notice that when p approaches infinity, this exponential becomes infinity, and 1 over infinity goes to 0. So limit p tends to infinity of fp is 0. Therefore, at infinity, this term is 0, and then at 0, notice that ap is 0. When p is 0, ap is 0. So the first term vanishes. First term vanishes, and integral this I1 becomes this. Now I1 is this. What is dA over dP? A is what is A? A is E P cube over T, and when we write E as A as square root of m square plus P square, then we have we are writing E as m square plus P square square root multiplied by P cube over T. Take its derivative with respect to P, and we get this. And I'm using the power of Mathematica here to do all these derivatives. Now we get put this value into this integral, and this integral becomes this. Then dp over dt is minus g over 6 pi square I1. So g over 6 pi square, 0 to infinity, and then we have this integral. And we have negative sign. Oh, okay, negative becomes positive. So yeah, this integral. Now what is next is, okay, and we can factor out 4 pi p square from here. and this would become g over 2 pi whole cube, and here we have fp 4 pi p square dp, and 4 pi p square dp I can write it as dqp. So I have g over 2 pi whole cube fp dqp. So you can see what I'm trying to achieve here. I'm putting it in the standard form where you have g over 2 pi whole cube, and then you have fp dqp, and in the expressions for pressure, number density, uh, and energy density. So they are of this form, that you have fp dqp and then a term here, and then you have g over 2 pi whole cube. So we have g over 2 pi whole cube, some term here, and then fp dqp. Now let us see what that term is, because we are trying to keeping this final outcome in mind. I am manipulating this because I know the answer, which is p plus rho. So of these two terms, one will become the expression for p, another will become the expression for rho. Let's see. Now this is p square over 3e, and I can factor out t here. So 1 over t comes outside. So I have 1 over t g over 2 pi whole cube, and if I put replace this by energy, I have p square over 3e. This is also energy, so I get E. And now what is this? P square over 3e is p square over 3e fp dqp is pressure, and E fp dqp is energy density. So I have partial derivative of p with respect to t is equal to p plus rho over t. And in this case, full derivative is same as partial derivative. So full derivative of p with respect to t is equal to p plus rho over t. Thank you.